After coming across the engineering and true stress-strain curves, let us come to the relationships between the engineering stress and strain with the true stress and strain values. Firstly, the relationship between true and engineering strain. We know that engineering stress, which is denoted by S, is equal to load P by the initial cross-sectional area, which is A0, and the engineering strain is equal to the change in length by the initial length or the original length, which is L0. So the engineering strain E can be represented as delta L by L0, which is the change in length by the original length, and which can be represented by the integration value from L0 to L, while L0 being a constant value remains outside the integration. So engineering strain, which is equal to delta L by L0, can be derived as L by L0 minus 1, which gives an important relationship, that is E plus 1 is equal to L by L0. This is a very important relationship which will be used in some later sections. Now let us come to the true strain or epsilon. True strain is actually the change in length by the actual or the instantaneous length, and which is summed up into small increments of length. So after summing up into small increments of lengths, it can be represented as the integration value of dl by L from L0 to L, where L0 is the initial length up to L, which is the actual or the instantaneous length. So this integration value is derived as log of L by L0. Now, since the volume of gauge length is expected to be constant, so by this conservation of volume, we get a relationship of A0 into L0, which is the initial volume, is equal to A into L, which is the volume at any instant of time. So from this relationship, we can get L by L0 is equal to A0 by A. Since the true strain epsilon is given by log of L by L0, so it can be rewritten as log of A0 by A, and which is equal to log of E plus 1, because we know that L by L0 is equal to E plus 1. So this is the relationship between the true strain epsilon and the engineering strain E, that is, true strain epsilon is equal to log of E plus 1. Next is the relationship between true and engineering stress. We know that true stress, which is denoted by sigma, is equal to load P divided by the actual or the instantaneous area A, whereas the engineering stress denoted by S is equal to load P by the original or the initial cross-sectional area A0. Now, the true stress can be evaluated from the engineering stress value. The true stress sigma, which is equal to P by A, it can be rewritten as P by A0 into A0 by A. Now, by the conservation of volume relationships, we already know that A0 by A is equal to L by L0 is equal to E plus 1, where E is the engineering strain. Now, by substituting the value of A0 by A, which is equal to E plus 1 in the original equation of true stress, the true stress sigma becomes P by A0 into E plus 1. Once again, we substitute the value of P by A0, which is actually equal to the engineering stress value. So, the true stress sigma becomes S into E plus 1, where S is the engineering stress and E is the engineering strain. Thus, the true stress can be represented in terms of the engineering stress and strain values. Let us come to the different salient points of stress and strain. In the earlier sections, we have already discussed regarding the significant points of engineering stresses, which are actually the different strength levels. For example, this is the yield point, where the strength is the yield strength, and this is the minimum stress level at which we get the measurable amount of plastic deformation, or in another words, from this point the plastic deformation actually starts. Next, from this yield point, the stress strain curve goes up through the stage of strain hardening and reaches the maximum point where the strength is ultimate tensile strength, or UTS, which is denoted by SU in this figure. This is the maximum stress which the material can withstand. Further, this is the start of necking, or the localized reduction in cross-sectional area. Coming to the engineering strain, we see the engineering strain is actually a measure of ductility of the material or percent elongation, and which can be recorded both in terms of uniform elongation or total elongation. Firstly, the uniform elongation is the uniform plastic deformation up to the UTS or onset of necking. In this figure, it is denoted by EU. The name uniform elongation stands for during this deformation, the tensile specimen will experience uniform increase in length and uniform decrease in cross-sectional area without any necking or localized reduction in cross-sectional area. Secondly, the total elongation or fracture strain is actually the total or the entire deformation up to fracture, and this is denoted by EF in this figure. Now let us come to the true stress and strain values. Let us first consider the point of maximum load Pmax, and let us denote the cross-sectional area over here as AU. Here the engineering stress is the ultimate tensile strength or UTS, which is equal to the Pmax divided by A naught, and the true stress, that is sigma u, which is the true stress at maximum load, is equal to Pmax by AU. From the earlier sections, we know that true strain is equal to the log of A naught by A, where the A naught is the initial or original cross-sectional area and A is the actual or instantaneous area. By considering this value of true strain and by representing the true stress and strain in terms of engineering stress and strain, we can derive that the true stress at maximum load will be sigma u is equal to Su, that is the ultimate tensile strength, which is the engineering stress, into A naught by Au, while the true uniform strain will be denoted by epsilon u, which is equal to log of A naught by Au. So thus we get the values of true stress at maximum load and true uniform strain. Next, let us come to the point of fracture, where the cross-sectional area is denoted as AF. So similarly, the true fracture strain or epsilon F will be equal to log of A naught by AF, which will again be equal to log of 1 by 1 minus R, where R will be the percent reduction in cross-sectional area. Lastly, if we consider only the necking stage, we see that the true local necking strain, which is denoted by epsilon n, will be equal to log of Au by AF, where AU denotes the area at maximum load and AF denotes the area at fracture. So these are the salient points of different engineering and true stress and strain values. After going through different parameters of material strength, let us come to the measure of material ductility. Now, investigation of material ductility is essential for primarily two purposes. Firstly, during the design stage, ductility provides indication of degree of plastic deformation before fracture, which means the more is the ductility, the material will give more chances with higher amount of plastic deformation before it actually fails. And secondly, during the fabrication stage, it indicates the degree of permissible deformation. Now, this is important because the metal working is essential for processing of many wrought alloys before their final applications. Now, following to the uniaxial tensile test, ductility can be represented as either of percent elongation or percent reduction in area. Firstly, the percent elongation is the percentage of plastic strain at fracture. This is the strain value which is denoted by E and which is equal to the change in length or the increase in length, which is equal to L minus L naught divided by the original length or L naught. So here L naught is the original gauge length of the tensile specimen and L is the length at fracture. In this figure, we can see that this is the gauge length of the tensile specimen before the tensile test, and this is the tensile specimen after fracture. So there is an increase in length which we can measure with respect to the original length L naught. Secondly, the percent reduction in area is denoted by R, and which is equal to the change in cross-sectional area, which is equal to A naught minus A divided by A naught, which is the original cross-sectional area. So here A naught is the original cross-sectional area of the gauge length and A is the cross-sectional area at the point of fracture. From this equation, we get a ratio of A naught by A, which is equal to 1 by 1 minus R. In this figure, we can see a tensile specimen before the test, and this is the same specimen after fracture. Now, due to necking, there was a localized reduction in cross-sectional area, and we can measure this reduction in cross-sectional area with respect to the original area or A naught. So these are the two parameters by which ductility of a material can be represented. One with respect to the increase in length and another with respect to the reduction in cross-sectional area of the gauge length. So the ductility of a material can be measured by both the parameters of percentage elongation in length and percentage reduction in area. Now let us discuss about the significance of these two parameters. The value of percentage elongation is generally dependent on specimen gauge length because a major portion of plastic deformation at fracture is restricted only to the necking region. With shorter gauge length, fraction of total elongation from necking is higher and subsequently increasing the percentage elongation value. On contrary, the percentage reduction in area does not depend on either of the initial length, that is L naught, or the initial cross-sectional area, that is A naught. Thus, percentage reduction in area is more significant in measuring ductility of a material. The significance of percentage reduction in area is evident from these figures. We can see that this is a tensile specimen of a comparatively brittle material, and this is another tensile specimen of a comparatively ductile material. We can see that due to necking, the localized reduction in cross-sectional area is much more prominent in the ductile material compared to the brittle sample. Same for the second figure, which is an aluminium sample. Aluminium is a comparatively ductile material, and so due to necking, the localized reduction in cross-sectional area before fracture is much prominent, which gives a measure of percent reduction in cross-sectional area or the ductility of the material. The values of percentage elongation in length and percentage reduction in area are generally different for a particular material, and this is evident from the relationship between these two. We see the percentage elongation in length denoted by E is equal to the change in length, that is L minus L naught, divided by the original length L naught. Here L by L naught is substituted by A naught divided by A due to the conservation of volume. And again, the ratio of A naught by A is equal to 1 by 1 minus R, where R is the percentage reduction in area. So ultimately we get the relationship of percentage elongation in length, or E, is equal to R divided by 1 minus R, where R is the percentage reduction in area. Now, strain in a material may be either an elastic or a plastic strain. Different materials may exhibit different proportions of elastic and plastic strain as a measure of ductility. So let us come to few important facts regarding this elastic and plastic deformation. Here in this figure we see an engineering stress-strain curve. This portion is the elastic portion which ends with point B or the yield point. Yield point gives us the value of yield strength, which is the minimum value of stress level at which we get a measurable amount of plastic deformation. So this yield point indicates the start of plastic strain. Within this elastic region, we see this point A, which is the proportionality limit, up to which the stress is proportional to strain following the Hooke's law. Now, this entire blue portion up to this yield point indicates the elastic region, and this deformation up to the yield point is the elastic deformation. Next, after point B or the yield point, the stress-strain curve moves up through the stage of strain hardening, reaches the maximum value which indicates the ultimate tensile strength or UTS. This is actually the maximum stress which the material can withstand. Now this point D is further the start of necking or the localized reduction in cross-sectional area, due to which the stress-strain curve comes down and ends at point E, where the fracture occurs. So this entire yellow region up to fracture is the plastic region, and this deformation up to the fracture point is the plastic deformation. Now let us check out few significant differences between the elastic and plastic deformation. Firstly, the elastic deformation is reversible or recoverable on the release of load, while the plastic deformation is not recoverable on the release of load, and hence it is permanent. Secondly, elastic deformation depends on initial and final states of stress and strain, while the plastic deformation depends on the loading path. Now, regarding this point, we will study about few important facts like hysteresis behavior or Bochinger effect in some later sections. Next, we see that within the elastic deformation, stress is proportional to strain. So, up to this point A, the stress strain curve is approximately a straight line, which indicates that stress is proportional to strain following the Hooke's law. While during the plastic deformation, no simple relationship between the stress and strain exists. And lastly, during the elastic deformation, there is no strain hardening effect, while during the plastic deformation, we see the strain hardening effect. That is, after the yield point B, the stress strain curve moves up due to the phenomena of strain hardening. Now, we have learned that ductility of a material can be represented by both the parameters of percentage elongation in length or percentage reduction in area. The percent elongation may again be recorded both in terms of uniform elongation and total elongation. So, the uniform elongation is a uniform plastic deformation up to the point of ultimate tensile strength or UTS or the onset of necking. So, in this figure, it is indicated by EU. The word uniform because during this elongation, the tensile specimen will experience an uniform increase in length and uniform reduction in cross-sectional area without any necking or localized reduction in cross-sectional area, which actually happens after the uniform elongation. And secondly, the total elongation is the total deformation up to fracture. So, in this figure, this is indicated by EF. So, these are the different measures of ductility of a material. Since we have come across the elastic and plastic strain, it is now time to introduce two more related and significant parameters called the resilience and the toughness. Firstly, the resilience. Quantitative measure of resilience is given by the modulus of resilience, which is denoted by UR. Modulus of resilience is the strain energy necessary per unit volume to deform a material up to the yield point of the material. So, it is actually the strain energy required by unit volume of the material to get deformed up to the yield point or within the elastic region. This modulus of resilience is generally represented by the area under the elastic region of the stress strain curve. In this figure, we can see that this is the pink highlighted portion, which is the area under the elastic portion of the stress strain curve. Secondly, the toughness. Toughness is the capacity of a material to absorb energy and plastically deform before rupture or fracture. Now, toughness is in turn represented by the modulus of toughness, which is denoted by UT. Modulus of toughness is a measure to the amount of energy absorbed by per unit volume of a material before fracture. Thus, the modulus of toughness can be represented by the total area under the stress strain curve up to final fracture or failure. In this figure, it is represented by this blue highlighted region under the stress strain curve. So, these are the quantitative measures and the graphical representations or approximations of resilience and toughness. Let us now come to the mathematical approximations of resilience and toughness. Firstly, the modulus of resilience. Now, we know that resilience is represented by the area under the elastic region of the stress strain curve. In this figure, it is denoted by this red highlighted portion. Now, if we calculate this area can be approximated to a right-angled triangle where the height is the yield strength denoted by S0 and the base is the elastic strain up to the yield point, which is denoted by E0. Thus, the modulus of resilience, which is denoted by UR, becomes the area of this right-angled triangle, which is equal to half into S0 into E0. Now, if we substitute the value of this strain E0 in terms of the yield strength S0 and the elastic modulus E, then the modulus of resilience becomes S0 square divided by 2 into E. Next is the modulus of toughness. Let us first consider for ductile materials. For a ductile material, we know that the stress strain curve has prominent stages of elastic region, strain hardening and necking. Here in this figure, we can see that the stress strain curve moves up through the elastic region up to the yield point, where the strength is the yield strength, Then the curve moves up through the stage of strain hardening up to the maximum strength, which is equal to the tensile strength, which is the start of the necking or the localized reduction in cross-sectional area, and after that, due to necking, the stress-strain curve comes down until fracture. So this is the typical stress-strain curve for a ductile material. Now we know that the toughness is represented by the entire area under the stress-strain curve. In this figure, we can see that this area under the stress-strain curve is approximated to a rectangle, where the one side of the rectangle is approximated to the value of the tensile strength denoted by SU, and the another side of the rectangle is considered to be the fracture strain, which is denoted by EF. Thus, the modulus of toughness, which is denoted by UT, approximately becomes SU into EF. Now, since the value of the yield strength, which is denoted by S0, and the value of the tensile strength, which is denoted by SU, these two values are not equal, so the area of the rectangle can be better approximated if we consider the side of the rectangle or the height of the rectangle to be the average of these two values, that is, the average of S0 and SU. So, for a ductile material, the modulus of toughness approximately becomes S0 plus SU by 2 into the fracture strain of EF. Coming to the brittle materials, we know that unlike ductile materials, for brittle materials, the plastic deformation is negligible. So, this figure shows the typical stress-strain curve for a brittle material. For a brittle material, the modulus of toughness UT is approximated to 2 by 3 into SU, that is the tensile strength, and into EF, which is equal to the fracture strain. So, this gives the mathematical approximations to the modulus of resilience and modulus of toughness. From the earlier explanations of toughness, it is now clear that in order to be tough, a material must be both strong and ductile. In other words, the value of toughness depends on both strength and ductility. This is evident from the given figure, which indicates a comparison of stress-strain curves for high and low toughness materials. Here in this figure, we can see two stress-strain curves. The first one belongs to the high carbon spring steel. Here, the strength level is higher, while the ductility or the elongation up to fracture is low. The second stress-strain curve belongs to the structural steel or the mild steel. Here, the strength level is comparatively lower compared to the first one, while the ductility or the fracture strain is much more higher compared to the first one. Now, we know that toughness is represented by the entire area under the stress-strain curve. Hence, for the second stress-strain curve, that is for the structural steel, even if the strength level is low due to high amount of ductility or fracture strain, the area under the stress-strain curve becomes much more higher compared to the area under the first curve. And hence, the structural steel has a higher value of toughness compared to this high carbon spring steel, even if this high carbon spring steel may possess a higher level of strength. So this indicates that the toughness value depends on both the parameters of strength and ductility, and a high strength material does not necessarily possess a high value of toughness.